Most microcomputer systems use a concept known as the matrix to control, or be controlled by, various peripheral devices. Keypads, displays, and even the tray system in the snack merchandisers, as well as applications for other merchandisers, are all examples of matrix devices. A matrix can be pictured as a grid with vertical and horizontal lines that intersect in a symmetrical pattern. The points where the lines cross represent an input, such as switches, or an output, such as motors or digits in a display, to the microcomputer. The advantage of a matrix system is the ability for the microcomputer to control a large number of devices with a relatively small number of control lines. For instance, the snack merchandisers can operate as many as 80 different motors with only 21 control lines. Think of a matrix as a chart or table. A number of rows and columns are used. To find a particular cell, one row and one column are selected. Where these two lines meet, we find the desired result. In this example, a 4x4 matrix is used. If column 3 and row 2 are selected, the point at which they intersect results in the answer brown. Notice the table has 16 colors, but only 8 lines, 4 rows and 4 columns. By using the same principle, the microcomputer can use 2 signals, one row and one column, to turn on a display, operate a motor, or read a switch. All Crane Merchandising Systems merchandisers use a switch matrix to determine selections. The standard selection panel is made up of 21 buttons controlled by 10 lines. Each column line receives a signal from the control board. These lines are strobed 60 times per second so that when column 1 is on, all other column lines are off. When column 1 turns off, the column 2 line turns on, and so on throughout each of the column lines. When the last column line turns off, column 1 turns on again, and the process is repeated. The 7 row lines are used to detect when a button has been pressed by sending the line low, or to ground. The microcomputer sees the strobe signal from the column line being fed back through the low row line and determines which button has been pressed. For example, if the control board observes the column line 3 strobe on the row 2 line, it would be determined that the F button had been pressed. Since a matrix cannot directly control AC motors, the snack merchandiser uses 24-volt DC motors. Remember that for a matrix to work, both row and column signals are required. In this case, the row controls the DC ground to the motor, while the column controls the plus 24 volts DC power. The Snack Center 1 is capable of handling up to 7 trays with 5 or 10 selections per tray. The Snack Center 2 can handle 4 to 8 selections per tray depending on the tray configuration. In addition, a 5-selection gum and mitt unit and 5 additional selections not presently used are available for a total of 80 possible motors. The matrix consists of 5 column lines and 16 row lines. In order for any motor to run, both column and row signals are needed. Candy trays use 2 row lines for control. The motors are organized in terms of odd and even. The even-numbered row is connected to all even-numbered selections. For example, row D0 is connected to D0, D2, D4, D6, and D8. Odd-numbered rows are connected to odd selections. So D1 is connected to D1, D3, D5, D7, and D9. This system is very effective with snack trays. A factory-built snack tray only uses 5 motors, but rather than numbering the selections as 1 through 5, each snack selection uses an even number, 0, 2, 4, 6, and 8. This means that only a single, even row line is necessary. In standby, the row lines will read approximately plus 12 volts DC. When a motor runs, the row line goes to a ground or 0 volts level. For example, to run the motor for the A0 selection, column 1 is energized, putting plus 24 volts DC to all 0 and 1 selections. Row A0 even goes low, putting DC ground at even motors A0 through A4. Since motor A0 is the only one having both plus 24 volts DC and ground applied, motor A0 runs. The entire motor matrix is designed such that only one motor can possibly run when any one pair of row and column lines is active. Now that the method of running motors has been defined, we must have a method to stop the motor when it reaches a full cycle. The controller must be able to monitor when the motor is in the home position. The cycle sense circuit addresses this.